And before we conclude, whatever we spoke here is, number one, there are threats from quantum computer towards cryptographic problems. That is about PQC. Okay, we spoke about PQC. Now what we are talking is about quantum cryptography. What is quantum cryptography? I said in the beginning, how do you use quantum principles? What are the quantum principles? Number one, qubits, and qubits, quantum gates, quantum registers, etc., etc., and all that. Along with that, I have quantum principles such as superposition, entanglement, etc., etc. How do I use them for building security solutions? How do I use them to build security solutions? What are the security solutions? Number one, either I try to get confidentiality, integrity, authentication. On top of that, you have one fundamental problem why we are going for asymmetric key schemes. What is that fundamental problem asymmetric key schemes are solving? Key management, right? What is that key management? When two people like Alice and Bob wants to interact, they wanted to have a symmetric key. So for that purpose, we went to a symmetric key scheme, and asymmetric key schemes are now having the threat from quantum. Imagine if that key distribution problem, if I am solving with the help of quantum computers, I need not go for asymmetric scheme, right? So I am going to address key distribution problem. So the question is how I am going to distribute the keys. When I say key, symmetric keys. So it is like this. So both Alice and Bob wants to have a common key. So how the common key gets established between Alice and Bob using quantum principles. That is called quantum key distribution. If I use quantum key distribution, which key I am establishing? Symmetric key. Once you have symmetric key, what algorithms you can use? AES, etc. Right? Okay. Before we go to this one, you need to understand that we are going to exploit the quantum principles such as quantum superposition, entanglement. I have shown you superposition, right? A bit, qubit in a state of both 0 and 1, and one qubit is interacting or entangled with another qubit. Right? This is how it goes. Alice wants to send Bob and establish the quantum key. Now here there are two channels. So far we are talking about one unsecured channel, which is already there. This is unsecured channel, public channel. On top of that, there is another channel called quantum channel. Okay. In this quantum channel, what happens? Alice is going to send the Bob, what he is going to send is qubits. Okay. This particular key, whatever this key is encoded as qubits. How these qubits are encoded again in the quantum computer is through photons. What is a photon? It is, you can think it as a light ray, okay? Light of particles, okay? A light source, a wave of particles of light. So it is like this. So imagine that I am just putting a torch like this. Okay. So see here, there is a light gets, right? When this light goes, it's not that this light is going like this. What this Alice did, Alice is going to use different polarizations. Okay. There is a concept called different polarizations. So is going to put a filter called a horizontal vertical filter to that light. So that filter good looks like this, horizontal and as well as vertical filter. There is one more filter or basis called diagonal basis. So he puts filter, horizontal vertical filter or diagonal filter. You understand? First I am sending 1 qubit. So the light goes, put horizontal vertical filter, first qubit. Second qubit changes my this filter. Third qubit I am just changing it randomly. The Alice is going to change this randomly. Okay. So this is how it goes. Okay. So you have horizontal, vertical, you call it as a polarization, okay, or a basis, or also you can call it as rectilinear basis, or else you can call diagonal basis. You can have the light goes through this particular basis. In this particular way, I can transmit 0 or 1, right? So when the Alice is using, this is Alice and Bob. When Alice is wants to send 1, he can send 1 either using horizontal vertical basis or diagonal basis. Similarly, Alice can send 0 either using horizontal vertical, that means rectilinear, or diagonal. Which one she chooses is her choice. Now the light goes, when Bob receives, Bob has to capture it. At that time, Bob also will use his own basis. When he is using a basis, it could be again a rectilinear basis or diagonal basis. Again, he uses randomly. It's not that since Alice has sent horizontal vertical basis, Bob is going to use same horizontal vertical basis. He may use that because you don't know what the basis Alice has used. Okay, Alice is using randomly basis, Bob is also using randomly basis. Now you see this. Okay, this is Alice and this is Bob. Okay, Alice is sending the bits 0, 0, 1, 0, 1, 0, 1, 0, 1. This is the bits. Look how she is sending. To send 0, what she used? Diagonal or horizontal, rectilinear? Diagonal basis she has used. So she's transmitted the light in this particular polarization state. Okay, as a diagonally, because 0. So see 0 diagonally. So when you see the diagonally, you see that it is 45-degree angle. Okay, 45-degree angle of diagonal, she is sending the light using the diagonal basis. What Bob did? What is the basis Bob has used? Vertical or horizontal, that means rectilinear basis. Obviously, will he be able to measure as same? No, because the basis is different. So he measured it as horizontal. What he got is 1. What he got is 1. Then don't come to this. Don't come to this now. Next, 0 she is sending. When she is sending 0, what she is using the basis? Rectilinear. And polarization angle, your 90 degrees angle. What Bob did? Same basis he has used, and hence he got same polarization angle, and the bit would be 0. You understand? Are you able to follow? Like this for all bits. Let us take last bit. 1. What is the basis? Rectilinear basis. Horizontal polarization angle, which is 0 degree. 0 degree horizontal what? Binary 1. Bob is using what basis? Rectilinear. What is that result he receives? 0 degree horizontal. Obviously, what is the bit he measures? 1. Done. Now, Alice has sent, Bob has measured. Now, point is, so far, Alice has sent, Bob has received. Now, the question comes probing. Alice will not tell what is the bit she has sent. Bob will not tell what is the bit he received. Alice will tell only the basis. Bob also will tell the basis. Basis they have used. So, in this case, Alice says, look, I used diagonal basis. Bob says, I used rectilinear. Gone out. Okay? Similarly, Alice says, I used rectilinear. Bob rectilinear. Matches? Yes. So, I take that bit as output, 0. Like this, you see wherever that matches, only those bits would be considered, 0, 0, 1, 0, 1. Like this, you transmit the entire key to the receiver and you probe. Once you probe, wherever the basis matches, only those bits would be considered, rest of the bits would be discarded. So, those bits that are considered would form the, what is this key? Symmetric. A key got exchanged. Have we used public key encryption? No. So, without using public key encryption, what is that we have used is quantum principles of transmitting light. So, there are a couple of questions would arise. Number 1, imagine if any attacker sits in between, captures the light, what will happen is your quantum phenomenon gets collapsed and hence, you will not have light getting received at the receiver side, errors gets introduced and hence, you will know that yes, there is an interceptor. It is not that attacker cannot be removed here. Attack can be happened. Advantage is that you will know that there is an attack. If you know that there is an attack, what you can do? You can discard that entire key. That's the advantage of quantum key distribution. Is it complete foolproof? Absolutely not. There are chances that this would actually, even if the bases are same, bits measurement may vary. See here, look this example. What is the polarization used? Diagonal. What is that is sent is 1. What is measured is 0. What is measured is 0. So, even if your basis is same, there are errors comes into this particular concept because of your errors in the measurement. Even this has to be handled. Okay, how they would be handled? Whatever the example we have seen is the sequence of maybe around 10 to 15 bits. Generally, it would not be. There would be large number of bits gets transmitted. Then randomly, some bits would be verified. Only those bits cannot be again considered for the key, they would be discarded. So, random sampling would be taken. In that sampling, they will check if there are any errors. Okay. So, that is what is mentioned here. If you see here, there may be, even if the transmission basis and measuring basis match, bit errors do occur. Okay. There are possibilities. So, it is not that the protocol is foolproof or error free. Still it is getting evolved. So, this is called BB84 protocol. That means this protocol is proposed when 1984. Okay. So, there are different versions and all that. So, point is that we are trying to manage, what we are trying to manage, which problem? Key distribution problem.